multiplication. We did not have to remember tables. It was very simple, but except that the result that we get, it requires larger number of bits to store. Next, in today's lecture, we will discuss about division and subtraction. So, for division, let us take 45 and divide it by, say, 9. And we know the answer should be 5. So just let's take 45. This is in the decimal domain, divided by 9. This is also in the decimal domain. And we know that the answer should be 5. And we know the representation of 45 because we had worked it out over here while we did the multiplication. So we'll just reproduce it as it is. We'll keep 45 here, 1, 0, 1, 1, 0, 1, 1, 1, 0, and we'll keep 9 here. 9 is 1, 0, 0, 1. Keep it here. 1, 0, 0. And we'll proceed exactly the way we studied in school, but now applying it to binary systems. So here 1, 0, 0, 1 will not go in 1. Okay, so this will not go. So we will have to bring down the next digit. Bring down the next digit, and again it will not go in this. So here also you get 0. So now you bring down the next digit. Here also it does not go. So again 0. So you subtract. And so here you get 1, 0, 1. You bring down the next digit. But now here it will go once. So when you the 1 here, it becomes 1, 0, 0, 1. So 1 into 9 is 9. And then subtract it. So 1 minus 1 is 0. 1 minus 0 is 1. 0 minus 0 is 0. 1 minus 1. I'm not writing this here. Now bring down the next digit, that is 0. 1, 0, 0, 1 does not go in this. So here you will have 0. Zeros are 0. So you will have 1, 0, 0. Bring down the next digit. So now it goes 1. So here you have 1, 0, 0, 1. Subtract and you get all 0. So remainder is 0. In this case, it's perfect division. So you can see here the answer is 5. And here you have your divisor. This is 9. This is in the decimal domain. And you have the part that is being divided. This is 45. This is in the decimal domain, and you have 5. I'm not considering the other digits here, they are not of significance. So essentially you have just 5 here, and this is quotient. So you can see that when you perform a division like this, you are able to get the answer correctly, and it's not a big deal. Remembering tables is not important. It's just simple multiplication by 1, that is just reproducing the bits, and then subtraction. So this is as far as division is concerned. Now we come to the task of subtraction. This is important, and we will spend some time on this. Let us take 9 minus 5. Both are in the decimal domain, 9 and 5. And we know the answer is 4. Now, if we represent the machine, see, for us to count by hand, from 5 we go on counting towards 9. So 6, 7, 8, 9, and we say that there are 4 counts necessary to reach 9, and so we place 4 here. Now this is okay for us because we have 10 fingers. But for the machine, it's just zeros and ones. So the machine does not do subtraction the way we do over here. It follows a slightly different approach. What is that approach? Subtraction is performed using addition itself. So you are going to add minus 5 to plus 9, and the result is going to be 4. So how are you going to do this? We'll follow, I'll give you an example of, for this we'll need the representation of negative numbers. How do we represent minus 5? Minus 5 in binary. So a machine performs subtraction by addition of a negative number. Okay? So this is important. You will have to keep this in mind that conventionally the subtraction doesn't proceed like this. Machine performs subtraction by addition. The addition of a negative number. Now, naturally, this raises the question: how do you represent this negative number? So let's see this representation of negative numbers. Save what we have done so far. We go to the next slide. So here we'll go to representation of negative numbers. Now, the representation of a negative number depends upon the size, the may say the number of digits, or in binary, the number of bits of representation. So let's say that you are using only one digit. Let's first do this for let's do it for decimal systems. The point is that it depends upon the size, on the bit size of representation. So this depends on size, and this size actually is in terms of bits, size of representation. Now, what do we mean? Let's start with an example of subtraction using addition in the decimal system. When we have the decimal system, um, let's take, let's subtract 9, let's subtract 5 from 9, and we know the answer is 4. Okay, because we count 5, 6, 7, 8, 9, and we say that 4 counts to 9. There's another way in which you can do by representation of a negative number. So to 9, you add minus 5. But for a one digit number, how do you represent a negative number? This is the question. So what we will do is we'll determine what is the negative of 5. So the method for this is we will have to determine a tens complement. But what is a tens complement? So first we will have to find a nines complement. Now we have over here 9 as it is, okay, and 5. Now what is a nines complement of 5? The number of bits that are remaining, the number of values that are remaining, if you take out 5 from 9, so you have 4. So 4 is actually equal to the nines complement of 5. Just a moment. Please give me a moment. I just yeah. So you have nines complement of 5, that is 4. So if you complement 5 from 9, you get 4. And to this nines complement, if you add 1, you will get the tens complement. So tens complement is just obtained by adding 1. It's just obtained by adding 1 to it. So if you add 1 to 4, you will get 5. So in a single digit representation, 5 is actually the negative representation of minus 5. It's a negative representation of 5. So now you take 9 and to that you add this minus 5. We are going to add, okay? So we'll get 9 plus 5. 9 plus 5. You see, this is actually equal to negative negative of 5 minus. So when you add, you get 14. Okay. Now, because you're dealing with the representation in only one bit, you have to retain only one bit, one digit, and chop off the other excess digits. You're left with 4. And so this is telling you that your answer is actually equal to 4. And it agrees with this. So what you did was you took 9 as it was, but you represented 5 as a tens complement. First you obtained the nines complement, then you added 1 to it, so you got 5, and then you added 9 with the negative representation of 5, which is plus 5, and you got 14. And because the representation has to be in just one digit, the other digit which comes out, that is chopped off. So you get just 4. And that is the answer that you have, 4. So this is what is done. Also, something similar is also done. Uh, so here we were just restricting to uh, one decimal. Now, suppose we um, want to try this out in case of binary systems also. So how do we proceed for binary systems? Let's change the color of the pen. So for binary systems, the procedure is exactly similar. So we take 9 as it is, 1, 0, 0, 1. So this is equal to 9 plus 9. And we have 5, that is 0, 1, 0, and this is 5. Now this is the representation in the decimal domain. And we are going to add to 9, we are going to add the, but now we don't say the tens complement, we say the twos complement of 5. Okay. So how do we obtain the twos complement? It's exactly the same thing. So we take 5, we determine the ones complement, and this is very easy. So wherever you have a 0, so you have taken 5 here, okay? It's represented in 4 bits. So you take, what is the complement of 0? Ones complement of 0? It is 1. What is the ones complement of 1? It is 0. What is the ones complement of 0? It is 1. Ones complement of 1 is 0. So this is actually equal to ones complement of 5. But we have to determine the 2's complement. And for 2's complement, we just add 1 to the 1's complement. So 2's complement for this, you just add 1. So if you add 1, you get 1, 1, 0, 1. So this is actually the negative representation of 5 in 4 bits. This actually is negative representation. That means I would say rather it's a representation of -5. That would be more meaningful. So let's say it's a representation of -5 in a bit size of 4. In 4. Okay, so you have got -5. So you have got 9. 9 is 1, 0, 0, 1. This is 9. And you have got 1, 0, 1, 1, which is -5. And you are going to perform an addition. Okay, so you're going to add. So when you add, you get 1 plus 1, that is 1, 0. So you place 0 here and you carry 1. 1 plus 0 is 1. 1 plus 1 is 1, 0. You place 0 here, carry over 1. 1 plus 0 plus 0, that is 1. And here you have 1 plus 1 is 1, 0. Place 0 here, carry over 1. That carry over 1 will place here. But because we have a bit representation size of 4 bits only, we will consider only 4 bits. And we will chop off the bit on the left hand side. So this part gets chopped off, just like we did in the decimal system. And we are left now with 4. 0, 1, 0, 0. And this is actually equal to 4. So you can see that we have performed the process of subtraction by addition of a negative number. Now comes the question of representation of this negative number. And so we will see how do we represent negative numbers in various domains. Uh, in the binary domain, if we have a large number of, if we have a different bit representation, how are we going to represent these numbers? So let us take the next slide. We'll save this work so far. Yeah. Now, I will ask some questions to the class in between, and I'll ask anybody at random, and I request you to keep your camera on when you're answering. Okay, so please pay attention to that, and you will be required to answer carefully. Okay. Now, let's see the representation of negative numbers. We had a slide earlier. We had a slide. Slide was yeah. So we will take this slide itself. We will copy this slide. Make a copy of it, and we'll again shift this slide a little below. Yeah. We can place it here. Now, I request you to keep your mics closed, mics shut off. There seems to be some interference. This is what we had in the different number systems. Now, let us take, let us see how do we represent 1, a negative of the number 1. Okay. So let us take the number 1. In 4-bit representation, the number 1 will be 0, 0, 0, 1. What we are interested in is how to represent -1. Okay. -1, how do we represent? Our representation size is going to be 4 bits. So -1 is represented as what? So we take 1 as it is, and we take the 1's complement first. 1's complement is, so this is equal to 1, that is, then we take 1's complement, that is 1, 1, 1, 0. This is 1's complement. And then we add 1 to it. So we'll get 2's complement of 1 is obtained just by adding 1 to it. So we'll add 1 to this, and we get 1, 1, 1, 1. So the number 1, 1, 1, 1 represents -1. So this number here, it represents -1. So in the same way, we can try out for -2. So -1, you can see over here, we have 1, 1, 1, 1. So this would actually be a representation of -1. Let's see representation of -2. So -2 is represented as what? How do you represent in binary? So you take 2, 0, 0, 1, 0. Okay. So this is actually 2 in the decimal system. You take 1's complement of it, 1, 1, 0. So this is just 1's complement of Then you add 1 to it, you will get the 2's complement. So this is 1 plus 1 is 1, 0. So place 0 here, carry over 1. So 1 like this. So here you have 1. So you can see that this is actually, so this gives you the 2's complement. 2's complement of, and it is actually also representing equal to minus 2. And you can see the pattern is here 1 1 1 0. So this is actually minus 2. If you do this for minus 3, minus 4 and so on, okay, you keep on doing this, you will find that you will get patterns like this: minus 3, minus 4, minus 5, minus 6, minus 7 and minus 8. I'm going to stop at minus 8. It's because we will have 8 numbers from 0 to 7 which are positive or 0, and we will have 8 numbers which are negative. Okay, so the positive numbers will be 0, 1, 2, 3, 4, 5, 6 and 7, and the others are negative numbers. Now on the left hand side we went from 0 to 15, and on the right hand side we are going just from 0 to 7, and then from minus 1 to minus 8. Now this representation is actually called signed representation, signed integers, signed representation. And this is actually unsigned representation, unsigned. You must have come across this word, signed representation. But this representation is in 4 bits. Okay. So this is how you can represent negative numbers. Negative numbers. So one important aspect of these negative numbers, how do you recognize whether a number is negative or not? If you see the binary representation of negative numbers, your negative numbers minus 8 starts from here. And you can see that all these numbers, negative numbers, they have a most significant bit. This is the leftmost bit, and this most significant bit you can see all these are 1. So you are proceeding uh, exactly like this. All the negative numbers have 1 in their most significant bit. Okay, this is a very easy way of remembering it. And of course the counting starts from here. So minus 1, minus 2, minus 3 and so on like this. We go on decrementing. Now let us see the representation for 8-bit numbers. Suppose you are provided unsigned 8-bit integer. So I would like to know from you, how are we going to proceed for 8-bit numbers? We'll say what we have done so far. The procedure is almost exactly the same. So we'll make this observation also here that uh, most significant bit. Okay, we'll write this as most significant bit. Uh, this bit on the extreme left, this is actually the most significant bit. And the bit on the extreme right, this is the least significant bit. Okay. So here the most significant bit is 1 or signed integer representation. Okay. So we will proceed to the next slide. We'll save our work, what we've done so far. We have some more time. I think 10 minutes are there. Yeah. So now let us consider, let's just extend our discussion to unsigned 8-bit representation. And this is more common when you are dealing with 8-bit microcontrollers or microprocessors. So how do you represent unsigned 8-bit integers? So we know that um, we can, for 8 bits, we can start with all the zeros. 0, 0, 0, 0. So 4 bits and then another 4 bits. One nibble and another nibble. So 2 nibbles make 1 byte. So this is 1 byte. You already know this terminology. This is, and we will go on incrementing this. So we'll have 0, 0, 0, 0, 0, 0, 0, 1. So this is representing 0. This is representing 1. Um, 0, 0, 0, 0, 0, 0, 1, 0. This is representing 2. Now you can go on like this. You can go on like this till you have 0 here and all the other numbers are, all the other bits are ones. What is this number? So if you work out the weightages and determine, you'll find this is 127. 127, and this is in the decimal domain. Okay, so we proceed like this, go on representing. So this is the binary representation of 127. But when you come to signed integers, the moment you put a 1 here, the integer becomes negative, the number becomes negative. So the next, when you add 1 to this previous one, you get this. Okay. And then you can go on adding 1, 0, 0, 0, 0, 0, 0, 1. Okay, you can go on like this. Uh, so this will be minus 128, and this will be minus 127. Okay. How do you start? You start with all negatives. 1, 1, 1, 1, 1, 1, 1, 1, and this is corresponding to minus 1. Then 1, 1, 1, 1, 1, 1, 1, 0. This is minus 2. Similarly, 1, 1, 1, 1, 1, 1, 1, 1, 0, 1. This is minus 3. So you can see that the negative numbers, all these negative numbers, they have their most significant bits, they are ones. Okay. And so this is the positive part, 0 and the positive integers. So these are positive integers, and these are negative. So these are, how do you represent the negative of 1, negative of 2, negative of 3 in the binary domain? So if you want to perform 9 minus 5 using 8-bit representation, okay, using 8-bit representation, we know that this is equal to 4 in the decimal domain. So 9, if we are doing 8-bit representation of 9, that will be 0, 0, 0, 0. Here you will have 1, 0, 0, 1. Okay, so this is 9. And you will have to determine minus 5. How do you determine minus 5? So you first write down 5. 5 is 0, 0, 0, 0, 0, 1, 0, 1. This is 5. You determine the ones complement. So this is 1, 1, 1, 1. Wherever there is a 0, you make it 1. And wherever there is a 1, you make it 0. 1, 0, 1, 0. This is ones complement of 5. And then you add 1 to it. You add 1 to it, so you get the 2's complement of 5. But in 8-bit representation. So this is now 1, 1, 0. And here you have 1, 1, 1, 1. So this is actually representing minus 5 in 8 bits, minus 5. And this is 8-bit representation. So if you add 9, 0, 0, 0, 0, 1, 0, 0, 1, and you add minus 5 to it, that is 1, 1, 1, 1. 1 0 1 1. So this is 9 and this is -5. These are in the decimal domain. This is in the binary. Now you just add this. So when you perform this addition, you get 1 plus 1 is 1 0, carry over 1, 1 plus 1 is 1 0, so sorry, I'm sorry. So 1 0, so 0, carry over 1. Again 1 plus 1 is 1 0, carry over 1, 1 plus 1 is 1 0, carry over 1, 0 carry over 1, 0 carry over 1, 0 carry over 1. So you will have a 1 carry here. But because you are doing 8-bit representation, so you will have to chop off this excess bit over here and you are going to get 4. Okay. So this is equal to 4. So 9 minus 5 is 4. This is how it's done using unsigned bits, unsigned representation. Now I have a question for all of you. I want all of you to do 5 minus 9. This is going to be equal to -4. So use this method and obtain 5 minus 9. Okay. So this is a small task for you. It's a small assignment. All of you should do this. Do it for 8-bit representation. Okay. So this is the task for all of you. You have to do this. 5 minus 9 is equal to -4. So we'll pause here for today and we'll proceed with Boolean logic and Boolean algebra and other things in the digital domain in our next lecture. So all of you been able to follow, I hope.
Yes,
Hello?
sir. Yes, sir.
Yes.
Yeah, okay.
Yes, sir.
There's something wrong. So we'll close the recording here.